Hey kids, Math here. Chapter 19, our final chapter of the year. This is it, kids. Acids and bases. I've got this broken down into 3 video lessons for you. The first one today going to be intro lesson, just discussing what acids and bases are, as well as labeling those conjugate acid and base pairs. Coupled compounds that are kind of related a little bit by acid and base behavior. Then our next video, number 2, will be pH calculations, and number 3 will be titrations between strong acids and strong bases. Let's hit it, get to this one. Acids and bases. To do this, we have to have some understanding. We've got to remember molarity. Molarity we did way back when in chapter 15, 16, where we did solutions. Molarity is going to be the number of moles per liter of a substance. Here's the setup for it. What's the molarity of a solution made when we put 12 grams of sodium hydroxide into a 500 ml total volume of solution? So what we need to do is find out in that 12 grams, how many moles are there? Take that 12 grams, divide by the molar mass. 1 mole, 40 grams. Where'd that number come from? Periodic table, pulled it right off of the chart on the wall. Okay, 12 divided by 40, I've got 0.3 of a mole. Now divide that by the total volume that's in this solution. 0.30 divided by 0.50, we're going to get a 0.6 molar solution of sodium hydroxide. Now, right now, that doesn't mean much to us, but in the next video on pH, that molarity becomes key. It becomes very important to us. Before we get there, let's talk a little bit about acids and bases. That acids are these things that have a pH that are less than 7. They're going to be sour. Sour Patch Kids, coated in citric acid, delicious and sour because they're covered in that acid. Is that a strong acid? No. Is that a weak acid? Yes. Is it concentrated? No, not very much. A little bit of citric acid gives those Sour Patch Kids their twangy little feel to them. Okay? These acids are going to turn a litmus solution red. If not a solution, litmus is an indicator solution that will turn red when it's acidic, blue when it is basic. It also can be used on paper strips, where we take a strip of paper, it's already been coated in litmus, and we dip that into our solution and find out how acidic it may be. Now, there are 2 reactions with acids that we want to keep track of. When we react an acid with a metal, that's going to happen in a single replacement reaction. When we react an acid with a base, that's going to happen in a double replacement reaction, and that's going to form a salt and water. You'll see more of these reactions in just a few minutes, okay? Conversely, bases, on the other hand, have a pH that's greater than 7, and they are very bitter. There aren't very many bases that we eat. They just don't have a very appealing taste to us, so we don't eat very much bitter. They turn litmus paper blue, and the biggie is these things are slippery, so things like Drano. If you've ever gotten a little bit of that on your hands, I don't recommend it, but if you ever did, it would feel very slippery, very oily in nature. So bases are simply that. Now, there are a couple different definitions of acids and bases. There are 3 definitions, as a matter of fact. We're going to talk about 2 of those. We're going to talk about Arrhenius definitions, and that's where it says that acids donate H+. All right, and what does that mean? It's going to donate an H+. It means that it's going to have an H in the front of the formula. That the very first thing in this formula you're going to see is an H. This is going to be something along the lines of HCl. H2SO4, HNO3. These all have H's to start their formulas off. That's how we're going to know that these are acids. If I have something like CH4, well, that's great. It has an H in the formula, but that H is not in front. It has hydrogen in it, but it is not acidic. All right, to be acidic, the H has to be in front, and by it being in front, that means it's going to split off pretty easily. Okay? Bases, on the other hand, the opposite of H is OH. And that OH is going to be in the back. And so these are going to be things like NaOH, KOH, CaOH2. It doesn't matter how many there are. Okay? The only time this doesn't come into play is if we have a very carbon-based compound, a molecular compound, something like CH3OH. Those are not really considered basic because they don't have the ability to donate that hydroxide. That because carbon is molecular and has a much lower electronegativity, it's going to share that hydroxide and hang on to it even tighter. So it's not going to be a good base. Now, one of the types of problems that comes up with acids and bases are called Bronsted acids and bases. Now, these Bronsted acids and bases are a little bit different than Arrhenius acids and bases. The acids are still the same. They're going to donate an H+, still the exact same thing. But the bases are going to accept an H+. And these end up forming pairs, two compounds, which are going to be very closely related by an H. And so if we take HSO4 minus and we put that into water, we find out that we get a sulfate ion, SO4 2 minus, and an H3O plus. Now, what we need to find out is which of these things are very closely related. Look, H2O and H3O are very similar. And HSO4 minus and SO4 2 minus are also very similar. What makes these two compounds differ is they've lost or gained a hydrogen. So in our case, this HSO4, it lost an H+, and the H2O gained an H+. And that's how Bronsted-Lowry defined these. And so if the HSO4 lost an H, it's an acid. And if the H2O gained an H+, it's going to be considered a base. All right, and we really can't tell that until we see what it forms on the product side of things. Okay, let's look at another couple of conjugate pairs here. Okay, so a conjugate acid or base is a product from a Bronsted-Lowry reaction. So if we take that same reaction we just had, HSO4, what was left over was the SO4 2 minus. Okay, so if the HSO4 was an acid, we're going to say that the SO4 2 minus is the conjugate base of that acid. Conversely, water gained a proton, gained a hydrogen. So it went from H2O to H3O. H3O is going to be considered the conjugate acid of water. The way you think of it, acid and bases are always on the left, conjugates are always on the right. Let's look at another one. NH3 is ammonia. We react it with water, and what we get is NH4 plus. Well, that's real similar to NH3. What did NH3 do? It accepted a proton, accepted an H. It gained an H. That makes it a base. The H2O lost an H. That's going to make it OH minus. So the H2O acted like an acid. It gave off one of their H's. And what's left is the conjugate base. Okay? Conjugates are what are left over after the acid and base have reacted. The acid donating, the H accepting. Now, what happens if you react water with water? It's not a trick question. One of the waters is going to act like an acid and donate and become OH minus, and the other one's going to accept and become H3O plus. These substances that can act like an acid or a base like water does, these are called amphoteric. They're kind of like amphibians. They can live in the water or they can live on the land. Amphoteric things can react as acids or can react as bases. And here are some common ions and compounds that have a tendency to do this. There aren't that many amphoteric species out there, but this is how you label conjugate acids and bases, as well as looking at some of their common properties, which would be sour, bitter, pH greater than, pH less than, as well as their reactions with metals and reactions with themselves. So I'm Smath, and I do hope that this recording helped you a little bit. In our next recording, we're going to talk about pH scale and calculations.